Every day, we are experiencing a large number of forces at different parts of our body. So, today's discussion is about the forces. The main topics we are going to see in this discussion are, let's start with different types of forces. The most important type of force and which occurs every time on us is weight. The person who first explained about gravitational force is Isaac Newton, and you know the story behind it. He explained why an apple is falling downwards. He explained it's happening because the apple is being pulled down by the earth with gravitational force. So every object will experience a gravitational force towards the earth, which we call the weight. The gravitational force always acts between the center of masses, means it should be drawn from the center of mass and towards the center of the earth. You can label it as weight or gravitational force, but not gravity. Gravity is a phenomenon, it's not a type of force. We can't imagine a life without weight, but there are some places you can experience weightlessness. This is a video taken from International Space Station, which is very far away from the earth. The next important force is normal contact force. What does normal means? From the way I have drawn the force, you can understand normal means perpendicular. Normal contact force should be always perpendicular to the surface in contact. For example, if you draw the apple on the earth, the normal contact force should be drawn perpendicular to the surface. It can be also called normal reaction. If something is moving on an inclined plane, then that should be the direction of normal contact force. Normal contact force is one of the most misunderstood forces. For example, when you are on a weighing machine, do you think the weighing machine can measure your mass? Is it showing actual mass? For example, if you are jumping onto the weighing machine, will it show the same reading? No, it will show a higher reading. Does that mean your weight has increased when you jump on the weighing machine? No. What increased is the push. You are pushing the weighing machine with a greater force. That force is the one it measures. So a weighing machine will never measure the actual weight or actual mass. What it actually measures is the normal contact force. What push you are giving to the weighing machine. But normally we take the normal contact force and the weight are equal because we are at rest. But is it true? No, because the earth is rotating. So we are not at rest. We are rotating very fast. So what you see on the weighing machine is not actually your mass. You will be actually heavier than that. Whenever you get any question to calculate the weighing machine reading, remember you have to calculate the normal contact force, not your weight. The next force is tension. Tension always occurs on strings. When a string is stretched or a body is compressed, always there will be tension. Now, how to mark the direction of tension? Here you can see two teams are involved in a game of tug of war. Let's consider person A. What will be the direction of tension on person A? As you can see, the person A will be pulled towards the person B. So tension should be always drawn away from the body. Like if you draw for the person B, it should be drawn towards the person A. Here there's only one string, so A and B will be experiencing exactly same tension. They will be pulling each other with exactly same force. Then what decides which team will win? If tension is going to be the same, then why one team wins? Which other force decides? So there's another important force acting here, which is very crucial in winning this game. That force is acting here, which is friction. So how much friction you get on your feet or shoes, that decides which team will win. The team with greater friction will always win. So next we are going to discuss about friction. Friction generally acts against the motion. For example, a football is getting stopped because of friction. This ladder is staying in that position without slipping is because of friction. So these are the directions of friction acting on the ladder. Is it true the friction will be always acting against the motion? For example, you are running. What's the direction of friction acting on you from the ground? You can see you are pushing the ground backwards with your foot. Means the ground is pushing you forward. So this is the force which keeps you in motion moving forward, and this is the direction of friction acting on you. So in this example, you are moving forward and the friction is also in the forward direction. So always you have to look at the point of contact. At the point of contact, how the body is moving. So at the point of contact, your feet is pushing the ground backwards. As a result, the ground will be pushing you forward. Next, we are going to consider some forces acting in fluids. A fluid means anything that can flow, like air and liquid together we call the fluid. What keeps the ships floating in water? There is an upward force acting on the ship, which is called the upthrust. Upthrust always acts upwards from the surface of a fluid. More details about upthrust is coming in the next topic, that is fluid dynamics. The same force even acts across the wings of an aeroplane to keep it in position. So there will be an upthrust acting across the wings. But generally we call this as lift force. Upthrust and lift force are exactly same thing, and this force is responsible for objects floating in a fluid. The next force acting in fluid will occur only when an object is moving through a fluid. Upthrust will occur every time, whether you are moving or stationary, every time upthrust will occur. But this particular force will happen only when something is moving through a fluid. Just like friction we have discussed, this force also will be always against the motion. Like this is the force which slows down a parachute. This force is called the drag force. So it's also called viscous force or sometimes viscous drag. Commonly we call it as air resistance or fluid friction. The difference between upthrust and drag is upthrust always acts whether a body is at rest or moving. Every time there will be upthrust, but drag force will act only when something is moving. Electric force or electrostatic force, which is the repulsion between two like charges or the attraction between two opposite charges. Then you have magnetic force, like like poles attract and opposite poles repel. Now we are going to draw these forces on diagrams, which is called a free body diagram. A free body diagram shows every force acting on a particular body. On. You should not draw any forces given by the body. Every force should be acting on the body. Let's consider a simple example. Earth rotating around the sun, and you are asked to draw the forces acting on the earth. There is only one force acting between earth and sun, that is gravitational force towards the sun. So this is called the free body diagram for the earth. Similarly, you can even draw the free body diagram for the sun. In that case, sun is being pulled towards the earth with gravitational force. So that's the free body diagram for the sun. Sometimes you will be asked to describe the forces. A description of a force should contain these details. It's acting on which body and who is giving the force, in which direction and which type of force, and magnitude if you know. For example, here it's exerted by the sun on the earth towards left side. You can even write towards the sun. What type of force? It's gravitational force. Magnitude, you may not know. If you know the magnitude, you have to write that also. So this is called the complete description of a force. Let's draw another free body diagram. You can consider the person and the chair as a single body, and we are going to draw all the forces acting on the body. That's called the free body force diagram. Always you can draw weight. Which other force is acting here? There will be tension. You are asked to draw the free body diagram for the kite. You are going to draw all the forces acting on the kite. I am sure there will be weight. If you have a doubt about which other forces will be acting, you can always think what would happen if only that force is acting. If only weight acts, the kite will fall towards the earth. But it's not happening. Means there is some force which is stopping it from falling downwards. That force is upthrust. Normally in equations of motion questions, like a ball is dropped downwards, we never considered the upthrust because upthrust is very small compared to the weight of the ball. But here that's not the case. Kite is very light, so upthrust will have a big effect on the kite. You can see there's a string and there's a force which always acts along the strings, that is tension. Now, if only these three forces are acting, what would happen? When you see the forces, you can see the resultant will be something towards the right side. But you know it's not moving to the right side. Means there is another force which is stopping it moving to the right side, and that force should be the drag force or air resistance or viscous drag. Now we are moving on to the next topic, which is Newton's first law. First law statement is very important. It says every object will continue its state unless it gets a resultant force or an unbalanced force. If an apple is on the earth, it will continue to be there forever unless you exert a force on it. Like that, if a body is going with constant velocity, it will continue with that velocity unless you exert a resultant force. Basically, Newton's first law deals with situations called equilibrium. Equilibrium has two possibilities, a body at rest or a body moving at constant velocity. Both these cases are called equilibrium. Let's see one example how Newton's first law is used in explanation questions. The question is why the car stops and the person moves forward. It's called inertia. But you will not get any mark if you just write inertia. You will need to explain what you mean by inertia. The first point is when the car is moving, the person is also moving with the same velocity. Now, when the car collides, a resultant force is acting on the car, not on the person. The person will continue his state of motion. Now we are going to see how to achieve equilibrium. There are two important conditions for a body to be in equilibrium. The first condition is every forces should be balanced. Means there should not be any resultant force. For example, if there is an upward force, there should be a downward force to balance it. But this is not the only condition for a body to be in equilibrium, because even if there is an upward force and a downward force, if the forces are not acting exactly at the same point, what happens is the body will begin to rotate. Then also it's not equilibrium. In order to stop rotation, this condition should be satisfied. Moment is the quantity which will make a body to rotate. If a body satisfies both conditions, then only we can say the body is in equilibrium. We are going to do calculations in each condition separately. We have already discussed in a previous video, so you can click the link to see that video. Let's see another question. A boat is in water and there's a sail. A fan is kept inside the boat and it's attached to the boat. You are switching on the fan. So the wind from the fan is coming and hitting the sail. The question is, will the boat move? So in order to answer this, you should know if there is a resultant force or not. If all the forces are balanced, it won't move. So let's draw all the forces acting on this system. System includes the sail, fan and the boat. One of the force is weight. I'm drawing weight of everything together, and opposite to weight, the force which stops it from sinking is upthrust. These are the upward and downward forces, but I'm not worried about them because motion is happening in the horizontal direction. So I want to know what are the forces acting horizontally and are they balanced. One of the forces is the wind hitting the sail. Fan pushes the wind pushes the sail. Is there any other force acting on our system? Remember, the fan is also part of our system. If you observe what happens near to the fan is pushing the air. So what the air will do? The air will push the fan back. According to Newton's third law, there will be a push on the fan by the air. So you can see there's a push to the left side and there's an exactly equal push to the right side. Means all the forces acting on this system are balanced and the boat will not move. So we have seen the first condition for equilibrium. Now we are going to see the second condition, that is clockwise moment should be balanced by anti-clockwise moment. Moment of a force is calculated as force into perpendicular distance is the most important part here. The distance what you measure should be perpendicular and one point you have to choose as the pivot. Let's do one calculation in moments. You can see a roller is attached to a string which is connected to a mass. The mass of the roller is given. The question is, if you attach a 50 gram somewhere on the roller, it will get balanced. It won't rotate clockwise or anti-clockwise. Means total clockwise moment will be balanced by anti-clockwise moment. So where you should hang that 50 gram mass. In order to find that, I have to calculate the clockwise and anti-clockwise moments. First step in finding the moments is drawing all the forces. So what are the forces acting on the roller? Weight always acts at the center of mass. Here the center of mass will be at 50 centimeter exactly because it's a 1 meter roller. Another force will be from the pivot on the roller, that is the normal contact force. A third force will be acting due to the mass suspended and it will be a tension. So these are the three forces acting on this system. Now we are going to find the clockwise and anti-clockwise moments. Means which forces will try to rotate the roller clockwise and which will try to rotate the roller anti-clockwise. What will be the moment caused by the force R? The moment of the force R will be 0 because moment is given by force into perpendicular distance. Here there is no perpendicular distance because the force is at the pivot itself. So if you see any force passing through the pivot, sometimes you may have to extend the force to see if it passes through the pivot. Any force passing through the pivot will create 0 moment. Means you don't need to consider any force passing through the pivot. Now let's think about W. It's not passing through the pivot, so it will be creating a moment about the pivot. So let's calculate the moment. It is calculated as force into distance. Mass is given as 100. I'm multiplying by G to get force into distance. I'm not converting gram or centimeter because it might be there in every term and I can cancel. So this is the moment created by W. Now let's see if it's clockwise or anti-clockwise. What you have to do is you need to bend the force towards the pivot to see if it is clockwise or anti-clockwise. You can see this direction. This is what you call clockwise, the direction in which a clock moves. So this will create a clockwise moment. Now I am finding the moment caused by T, the tension. So same equation, force is m into g into distance. Distance should be the perpendicular distance from the force to the pivot. The pivot is at 40 centimeter, so 40 to 100. That's why I have taken 60 centimeter. This is the moment. Now let's check whether it's clockwise or anti-clockwise. For that, I have to bend the force towards the pivot. So you can see this is going anti-clockwise. So we have a clockwise moment, we have an anti-clockwise moment. Let's see if they are equal. The total clockwise moment and anti-clockwise moment. But you can see his gram is there on both sides, centimeter is there on both sides, even 9.81 is there on both sides. So I'm just cancelling them. Clockwise I got 1000 and anti-clockwise I got 1200. That is 20 into 60. Means if you want to balance this roller, you need extra 200 clockwise. Then only the object will be in equilibrium and you have a 50 gram mass. So where do you suspend? You need a moment of 200. So 50 is the mass into distance should give you 200. Means the distance should be 4 centimeter. From the pivot, 4 centimeter from the pivot, and it should be giving a clockwise moment. Means same direction as the weight. It should not be on the other side. should be on the same side because we want both clockwise moments. So the 50 grams should be suspended at 44 centimeters. One more example. You want to find the resultant moment about the point P means the clockwise and anti-clockwise moments are not equal. There is a resultant. We need to find the moment of every force. Let's consider this 5 Newton first. Here the force is given 5 Newton and we want to find the perpendicular distance of the force from the pivot. But the pivot is actually far away from the force. In such situations, always what you can do is you can extend the force to reach near the pivot. So now it's coming in level with the pivot. Then I can measure the perpendicular distance. So total is 4 meters and 2 meters up to here means remaining should be 2 meters. So I'm going to calculate the moment. 5 Newton is the force into 2 meter is the perpendicular distance. So I got 10 Newton meter. Now I'm going to see if it's clockwise or anti-clockwise. For that you have to bend the force towards the pivot and you can see the direction it's going anti-clockwise. Let's think about the next force, that is this 10 Newton. Again the problem is the force is not close to the pivot. So I'm going to extend the force so that I can get the perpendicular distance from the pivot. So it's directly given there, it's 2 meters. I'm going to calculate the moment. 10 into perpendicular distance is 2, so I got 20 Newton meter. Is it clockwise or anti-clockwise? Let's bend the force towards the pivot in the shortest path. Okay, you should not be bending the force through this path which is longer path. So it will create again an anti-clockwise moment. Now let's think about the 50 Newton force. Again you have to extend the force because the pivot is far away. Then find the perpendicular distance. Directly you can measure from the bottom. It will be 3 meters. So force into distance. You will get 45 Newton meter. Now clockwise or anti-clockwise? Let's bend the force. You can see it's going clockwise. Means you have 45 clockwise and 10 and 20 anti-clockwise. Let's find the resultant. The resultant will be 45 minus 30, 15 Newton meter clockwise. This is a very famous statement by Archimedes. He was explaining the principle of lever using the principle of moments. He said he could lift the earth if you provide him a long enough pole. So let's see what he actually meant by that. Means what's the physics behind it. You can consider you are balancing the earth on a pole by applying another force on the opposite side, F1. The earth will be exerting a force F2. The force F1 need to be very big because the force the earth will exert, that is F2, will be very big force. But using the principle of moments, you can reduce the force F1. Let's see how. Let's take the distances D1 and D2 from the pivot to each force. The principle of moments says that the earth will be balanced and staying in that position if F1 into D1 is equal to F2 into D2. Now what you are going to do is, you are going to increase the distance D1. That's why he is saying to give a long enough pole. So as the distance D1 increases, according to the equation, F1 should decrease because the body is in equilibrium. As D1 increases, F1 will decrease. So you need to apply a very small force to balance the earth if you have a long enough pole. Now you can try these questions. You are going to tell, will the system stay in equilibrium or will it rotate clockwise or anti-clockwise in each of the following situations? In this situation, what will happen? In this situation, there is one mass and it is kept at a distance of 1, 2, 3, 4. But there is nothing to balance on this side. So if you calculate the clockwise and anti-clockwise moments, there is an anti-clockwise moment. I am taking F as the force given by this mass and the distance is d. Each distance is d, so total is 4d. So there is an anti-clockwise moment but there is no clockwise moment. As a result, the body will fall anti-clockwise. Next example, let's calculate the clockwise and anti-clockwise moments. In the anti-clockwise direction, there are two masses. So I am taking 2 times the force and both are kept at 2d distance. So totally I have 4 Fd. But on this side, the distance is 1, 2, 3, 4 and the mass or the force is just 1. So the total clockwise moment is one force into 4 distance. But you can see the clockwise and anti-clockwise moment both will give exactly same answer, means the body will stay in equilibrium. Third situation, there are two masses at different places, so the total anti-clockwise moment is 1 force into 4 distance plus 1 force into 1 distance. This is, and on the anti-clockwise side, there is 2 force together at a distance of 2d. So total anti-clockwise moment is 5 times f into d. This is 1 plus 4 times, so 5 times f into d. The clockwise moment is only 4 times, so it will fall again anti-clockwise. The last situation, two forces acting at different distances. So let's find the total clockwise moment. One force is at a distance of 4, other one at a distance of 3. So total 7 F into D. That's a total anti-clockwise moment. Now the clockwise side, 2 force, 2 distance. So 4 times Fd plus 3 times Fd means the clockwise and anti-clockwise moments are balanced. The object will stay in equilibrium. More examples of moments we will see in the next video.